going to do our monthly webinar. This month is the part 2 about thermodynamics with Jerome. So as always, the chat and Q&A is open. If you have any question, we will get to those at the end. So Jerome, you can go.
Thank you, Megan. All right, welcome everybody to today's webinar on the thermodynamic. Part one was the last month about like the heat pump, and basically we just focus on why we choose to build such a product. Why is it important for new technicians to know how to diagnose how those system works, learn about the strategy behind all those different mode where the car can both regulate the battery temperature and cabin comfort. So in this webinar, part two is going to be more about how does that thing actually work. So we're going to go through different scenarios. I like to say different strategies, because it is all about strategies. Okay. In the last webinar, we discussed that basically an heat pump is taking heat from somewhere and transfer it to another place, right? So it's all about the transfer of heat. And I said heat because we need heat to be transferred, right? So without heat, there's nothing to transfer. So at some point, we might need to create our own heat to be able to transfer that energy into other components that need that extra heat, or even for the cabin, for everyone to enjoy the ride, right? So before starting up with the different strategies, I want to talk about latent heat a little bit. I know in the last webinar we talked a little bit about latent heat, but this is a graph that I really like to show instructors, even students, so they can like see what exactly are we talking about when we say latent heat. And in that case, let's use water. Water, we all know water, right? So water have three states: solid, liquid, and gas. Same thing with our refrigerant. We can have liquid refrigerant, gas. So in that case, latent heat will be the moment where we want to change phase, where, for example, passing from liquid to gas. But here on the x axis, we can see energy input, which is basically heat, right? Energy. And then we have the temperature, right? So the temperature is going to be the temperature where my glass of water, for example, is right now. So whoop, there we go. So let's say I do have a glass of water. I'm heating up my glass of water. So I do add up energy to that glass of water. That's going to make the temperature of that glass of water raise. And at some point, I'm going to hit some sort of a plateau where I'm going to start changing phase and passing from liquid to gas. And at that moment, as we can see, we keep increase the energy input to that glass of water, but the temperature is going to stay the same. And that exact moment is what we call latent heat. So the reason why it's super important to talk about latent heat and understand what is latent heat is basically that the moment we are changing phase, we keep adding up energy. And that extra energy is going to be super useful for either subcooling, superheat, so to release that energy back to the system. Okay? Of course, like we talked to the last webinar, the actual product that we develop have side glasses on different heat exchanger. So it's super easy for you and the students to actually see well the phase changing in those heat exchangers. As we can see here, we do have side glasses every time we do have some sort of an heat exchanger. Here's our evap. That's going to be our cabin condenser. So the condenser that is actually inside the cabin of the vehicle. We do have side glasses at the inlet and the outlet of the chitter. So that chitter, whatever is in use, it's going to be part of our evap. So we're gonna be able to see the refrigerant changing phase inside the chiller itself. And same thing with the external heat exchanger. And why I'm calling it the external heat exchanger is because depending on the strategy, I'm going to be able to switch that component from an evap to a condenser. So this is why we call it heat exchanger. So we talk about latent heat. Of course, we're going to talk about superheat and subcooling, right? And I always love to do this little experiment with my class. Let's say, hey, we are in the classroom and the ambient air temperature is around 69 Fahrenheit or 21 degrees Celsius. I always like to ask everyone in the room, so based on your knowledge, are we breathing subcooling or superheated air? And then people start like, oh, I really don't know, or think about it. And there's a lot of time where people do not really understand what's subcooling or superheat. So in that case, I'm just go ahead and say, well, basically the air we're breathing right now in the classroom is composed of nitrogen and oxygen, right? And in that case, at atmospheric pressure, because we are not under pressure, right? We're still at atmospheric pressure. Well, basically at 14.6 psi. The evaporation point of oxygen at that pressure, atmospheric pressure, is going to be minus 310 degrees Fahrenheit or minus 190 degrees Celsius. So by just doing a little subtraction, so in our case, taking, for example, the ambient air temperature in the classroom, which is 69 degrees Fahrenheit, minus our evaporation point, which is at the same atmospheric pressure, minus 310, well, the air we are breathing, is actually superheated at 379.8 degrees Fahrenheit. So why is it important to really truly understand that? Is, well, basically, even at when it's super cold outside, there's still some heat to be captured. But there's a limit to what we can capture. And we're going to talk a little bit about that in a few slides. So superheat, subcooling, super important. So too many instructor, I should say, don't go that far with their student. They say, oh, it's too complex for them. But you really do need to understand superheat and subcooling, whatever you're teaching, traditional AC system and or heat pump system. So superheat, super important. Superheat is going to be important for the compressor to only have gas sucked in by the low side. So it's going to prevent any components to turn bad, and the subcooling will be super important for whatever the liquid goes to the expansion valve, the TXV, the EEV valve, which is electronic expansion valve. I mean, needs to be liquid, right? We don't want to have a mixture of liquid and gas, otherwise the system won't be performing like he should. So superheat and subcooling are super important concept that you need to teach. And using the product, it's going to be super easy for them to do it, because with those thermometer, they can go ahead and take temperature measurement everywhere on the heat exchangers. So the refrigerant slider, I like to use that app called Danfoss Ref Tool, which is available for free. And we like whatever an app, super useful app is free on our cell phone, or you can go to their website. And what is amazing with that app, let me go here. Let me go. Let's show you that here. There we go. So you can basically choose from any gas that is in your system. So in that case, we're going to use the R134A, and you're going to have all the specs related to that to that gas, right? But you can also use the slider here. So depending of the pressure that you're going to read on the low side and the high side, you can basically have a quick access to the the boiling point or the condensing point of the refrigerant. So if we go back to the specification of the gas itself, we can see that the boiling point at 0 bar is going to be minus 26 degrees Celsius, which you can basically switch minus 40.9 degrees Fahrenheit also. So you can switch whatever you prefer. But the thing is, like I said, there's still some heat to be absorbed even if it's super cold outside. But I mean, here in Canada during a winter, it can be below that. It can be like super cold outside. So in that case, our heat pump won't be able to heat the cabin, to capture heat, right? So the system will use some different strategies to build or find heat somewhere else than just outside, right? So if I'm going back to my presentation here, as we can see, we do have, that's a penthouse. So all the controllers for Tesla Model 3 high voltage battery. And as we can see on the top, we do have some cooling line. So we do have some coolant going through the high voltage battery and also some coolant going through those computers that are for example, the onboard charger, or in that case, that's ADAS computer. Those computers and the high voltage battery needs to be cooled down or heated up depending of the condition. But thing is, when those are hot and needs to be cooled down, we can use that extra heat from those components and take that heat and transfer it to somewhere else. Might be the cabin, for example, right? But the thing is, at some point, the heat that we can capture outside is not enough. And then we're going to use some different strategies to create our own heat. So that's our high voltage AC compressor, which is one of the most important component in an heat pump. That high voltage AC compressor basically is a brushless DC motor. So we do have an inverter that's going to convert the high voltage DC to a three-phase motor. As we can see here, we do have our stator. Here, that's the PCB board. But if you zoom in, you can see those three phases. So the W, the V, and the U. And those are all the IGBTs transistor that's going to be creating that three-phase for the motor itself. So it's a scroll compressor, which is variable. So that being said, because you can control that compressor, it's going to be super useful for all those different strategies, right? But that PCB board, that inverter needs to be cooled down. So the engineer think about it and say, hey, guess what? We're going to put that PCB board next to the low side port on the compressor itself. So we know that normally it's going to be gas, but like quite cold gas that's going to be sucked into the compressor by the low side port. So in that case, that low side will going to be cooling down that PCB board with the inverter. So it's going to be an extra superheat. So that being said, having extra superheat is going to prevent any liquid to go through that compressor. But because we do have that extra superheat from the heat captured by from that inverter, we already have some heat for the compressor to compress. So the compressor would have to work a little bit less, right? So it's all part of strategy of having a system that is super efficient. We also have, so whenever you have a three-phase DC motor, you're going to be able to control the field of the stator. So in that case, we have our AC compressor at the top here. We do have more and more blower fan that are brushless DC motors in standard vehicle. We do have our drive unit for any EV. So basically, we have that lossy mode where basically it's an intentional loss of heat or energy, which basically what you're going to do is desynchronize the phase of the stator. So it's going to be with the induction of the permanent magnet rotor. It's going to create a lot of induction, which means a lot of heat, a lot of energy. So running coolant to the heat exchanger for those motors, it's going to be able to capture a lot of energy, a lot of heat. So that's one strategy that is super useful, whatever it's super cold outside, and that the refrigerant um, is not able to capture any more heat from the outside because it's too cold outside, right? So then the car can generate his own heat. But I mean, you won't lose that heat because it's going to be transferred to whatever it needed to. Like I said in the last webinar, we also have the PTC heater, which is going to be a great source for heat, which is basically a PTC heater. It's a heater itself, but it's consume a lot of energy. And then in that case, whatever it's cold outside, super cold outside, you want to have most of the energy for the battery and for the range uh, of the car. So in that case, we gotta use different strategy before we can use that PTC heater. But that that component is gonna be there if we need to have that extra little heat. But the vehicle, the car is gonna be trying to figure it out its way to generate some heat before using the PTC and having a huge loss of energy. So going to the mode. So we do have the mode 1, which is cabin cooled. Cabin cooled is going to be like any standard AC system that we all have probably in our standard ICE car. Basically, we have a compressor that's going to be compressing hot vapor, right? High pressure vapor. We're going to go to the cabin condenser inside the cabin, but we don't want to have any heat going inside the cabin. We want to cool down the cabin. So there's not going to have any airflow. So the fans of that heat exchanger is going to be off. We also going to have the airflow shorter is going to be closed, so to preventing any heat going inside the cabin. So that being said, there is no heat transfer in that heat exchanger in that mode. So it's like having a long pipe. We're going to go here, bypass. So we are not going to use that EEV, that TXV valve, that electronic expansion valve. We're just going to go bypass. We're going to go to our external heat exchanger. In that case, that's going to be our condenser condensing our vapor into hot liquid. We're going to go up here to that expansion valve. So we're going to have a restriction creating our differential in pressure. So we're going to have a low side now, partial liquid and vapor. So we're going to go to the evap with a airflow. So that's going to absorb the heat from inside the cabin. So it's going to feel cool inside the cabin. But by absorbing the heat from the cabin, I'm going to evaporate the gas inside the evap. So it's only going to be gas sucked by the compressor to complete the cycle. So that's normal operation of any AC system. So now the next mode, we just flip things around. So now we want to heat up the cabin, but using the heat pump, not using any PTC heater, not using heat element. We're going to use the heat pump because if it's the heat pump is able to capture heat from outside, that strategy is going to be the more efficient. Okay, We are not going to use a lot of energy, but we're going to still be able to heat up the cabin. So we're going to have the compressor compressing, but now we want to have the heat dump inside the cabin. So we're going to have the fan for that heat exchanger turned on, and then the airflow shutter is going to be also turned down. So we're going to have the heat transfer, and the heat's going to go inside the cabin. So condensing, condensing, condensing. So now we're going to use that expansion valve, or that TXV, to have our pressure differential. So now we're going to have a low side going to that external heat exchanger, which is now the evap. And then we're going to capture most heat from outside the vehicle. And then we're going to use the bypass because we don't want any heat exchange with the evap inside the cabin. We want to heat up the cabin, not cool down the cabin. So it's just like a longer pipe, and go back to the compressor. So if we go back to mode number 1, so that's going to be our evap. So look at the size of that evap in the mode number 1 and the size of that evap in mode number 2. The mode number 2, the external heat exchanger, is going to be slightly bigger. The reason why is, like we said, it's still cold outside since we want to warm up the cabin, but there's still some heat to be captured, right? So having a bigger heat exchanger can be beneficial to capture heat. At a certain point, there's not going to be enough heat to be captured, and then we can rely on other system. But that's just flipping the system around, and that is the beauty of the heat pump. We can also have both expansion valve working together. So in that case, that's going to be still cabin heat, but we also want to have that defrost option. So the only difference, so we're going to dump all of our heat inside the cabin. So airflow shutter open, the fans for the cabin condenser is going to be turned on. We're going to have the expansion valve, the first expansion valve working. So we're going to have a pressure differential here. We're going to have the external heat exchanger that becoming our evap. Then we're going to still use the expansion valve here also, and having the evap fans turned on. So we're going to have both expansion valve working together, because we're going to have some heat to be captured here, but also some heat to be captured inside the cabin to defrost the windshield, for example. And then we're going to go back to the compressor. So those two valves is going to use a sensor at the outlet of the evap, and based on the superheat, they're going to adapt and work together. So both going to be able to have some sort of pressure differential. Mode number 4. Now we're going to use the only the glycol side, so the coolant side. So mode 4 is going to be warming up the cabin, but you know what? There is not enough heat outside the vehicle to be able to transfer to the cabin. So in that case, we can rely on the PTC heater. So having a pump pushing coolant through the PTC heater, which that PTC heater is now on, we're going to warm up the coolant. We're going to go inside the chiller, but the chiller is not turned on, so the coolant won't get cooled. So we're going to go out of the chiller, still warm. We're going to go through the heater core, which is part of the cabin. So we're going to go hot coolant inside the cabin core. So we're going to have fan that's going to allow some heat transferring. So we're going to dump our heat inside the cabin, and then we're going to go back to the pump again. So that's the cycle in case the heat pump itself won't be able to absorb enough heat. Now, another cool scenario is going to be cooling down the battery. Cooling down the battery is going to be super important. So now we're going to have both the refrigerant side and the coolant side working together to make that happen. So I know some manufacturer use only the AC to cool down the high voltage battery. But in that case, we are using coolant because we all know that the heat transfer is going to be 25% more efficient with liquid than just air. So more and more manufacturer try to use coolant for the thermoregulation. So in that case, we're going to have the compressor compressing hot vapor. We don't want to have any heat inside the cabin. We just want to cool down the battery. So in that case, we're not going to have any airflow, and the airflow shutter is going to be closed. So we are not condensing nothing. It's just a long pipe. We're going to go bypass that expansion valve. Now we're going to dump all of our heat outside the vehicle. So we're going to turn on the fan. So we're condensing, and then we're going to use that expansion valve right here. So as we can see, we have 3 expansion valves. That one is for the chiller. So now we're going to have our differential in pressure. So we're going to have low side. So that coil inside the chiller is going to be only refrigerant, not coolant. The coolant is going to be in the reservoir of the chiller, but inside the coil, it's going to be only refrigerant. So that coil is going to be super cold. It's going to absorb the heat from the coolant. So by absorbing heat from the coolant, the gas inside, well, the refrigerant inside the coil, it's going to evaporate. So we only going to have gas going back to the compressor. So in that case, the chiller is like the evap, right? Absorbing heat. So that's the refrigerant side. But let's go to the coolant side. So we have a pump pumping hot coolant from the high voltage battery that is too hot. We're going through the PTC, but that PTC is turned off. We're going to go inside the chiller. The glycol, the coolant is going to be cooled. So we're going to go coming out of the chiller as cooled coolant. And we're going to go force our way through the high voltage battery and then absorb all the heat from the high voltage battery. So all the heat's going to go back to the pump, go back to that chiller again and again and again. So this is how we're going to regulate the high voltage battery temperature, which is normally a good thing since we want to protect the high voltage battery for any runaway or and we want to keep the range of the vehicle quite high. The last mode I want to show you guys is this mode here. So here we can, so the magic with the heat pump is that we can cool down multiple components at the same time, or we can cool down one component and heat up one other component at the same time. So just because we have so many paths, so many expansion valves, we can create different scenarios. So in that case, mode number 10, I like to call this strategy the Arizona mode, which is super hot outside. So what we want to have is cool down the cabin, but the high voltage battery is super hot too. So I want to both cool down the cabin and cool down the high voltage battery. So in that case, if we want to do it, we want to have the compressor compressing. We're going to go to the cabin condenser. We don't want to have any heat inside the cabin, so no airflow, and the airflow shutter is closed. There's not going to have some heat transfer, so we're going to bypass that TXV. We're going to dump all of our heat outside the vehicle. We're going to use the first TXV valve here for the chiller, but also in parallel, we're going to use the other expansion valve. So let's start with the chiller. So we're going to have the TXV, the working. So that's as the chiller going to have some low refrigerant. So we're going to be able to cool down the coolant. But here we also have the expansion valve working in parallel. So we're going to have some low side from the evap with some airflow. So we're gonna be able to cool down the cabin and go back to the compressor. So people ask me, but using two expansion valve in parallel, is the systems going to be less efficient? I mean, you're not just using the evap like in the mode one. Now you're using an evap in a chiller. The truth is, well, maybe a little bit, but at the same time, it's going to be cold enough. So the pump is going to pump hot coolant from the high voltage battery going inside the chiller, and then force its way to the high voltage battery to cool down the battery. So hot glycol is going to be now using the radiator also because it's super hot. So it's going to be cooled by the radiator outside the vehicle, force its way to the chiller to cool it down again and again and again and again. So it's just amazing, all the strategy that the vehicle is gonna try to do to have a system that is, if well, I mean, that can perform enough, but sufficient enough so you're gonna enjoy your ride and have um, more and more range available for you in any condition, either it's super hot outside or super cold outside. So thank you, everyone. I don't know if there's any question in the chat, Meg.
No, we don't have any question for now. I'm gonna let you have a little time to type in, but as always, you will receive a certificate of participation for this webinar. You should receive it by the end of the week, and also you will have an email with the recording, and it will be posted on YouTube too. So that's it. If you have any question that comes up later, feel free to reach out and we'll be there to answer them. So,
All right. Thank you, everyone. Have a great
thanks,
day.
everyone. Bye bye.